get started. So today we'll be talking about decision trees and some generalizations of decision trees or extensions known as bagging and random forests. A couple announcements. Homework 2 is due tomorrow. Homework 3 will be released tomorrow sometime as well. It is going to be quite a bit easier than homework 1 and homework 2. Let's take a step back for just 1 second, or half a minute, and talk about sort of the topic overview and sort of where we are in this course and where we're headed, right? And so, we have thus far been looking at supervised learning, right? And most of this course will be on supervised learning. And within supervised learning, we've looked at primarily linear models, concepts like overfitting, different choices of loss functions, different types of learning algorithms, most notably stochastic gradient descent. As we move along in this course, we'll look at increasingly more nonlinear models. So this lecture, we'll be talking about nonlinear models, of which decision trees are an instance of. And then later on in the course, we'll look at unsupervised learning. So this will happen in about 2 weeks, where we don't have a target label. And then finally, we'll look at things like probabilistic modeling, which can be both supervised and unsupervised. And that's how we'll close the course, right? So that's sort of a roadmap of sort of the topic overview of what we've covered and where we're headed, right? And so this lecture, we're going to focus on decision trees, which is a model class that is nonlinear, right? We saw just a little bit of a nonlinear model class in the form of an artificial neural net, and we'll talk about that more next week. But for this lecture, we'll focus on decision trees, right? And the goal of using a nonlinear model class is, one of the goals at least, is to achieve the highest accuracy possible, right? And so this lecture, we'll be looking at decision trees and some extensions such as bagging and random forests. And then the next lecture on Tuesday, we'll be looking at boosting and ensemble selection, which are also motivated by things like decision trees. Okay, so decision trees. So decision trees are actually extremely self-explanatory. They're a very, very simple model class, at least conceptually, right? And so here is a decision tree. It is a binary decision tree in that every internal node in this tree has 2 children, right? So literally what happens is you have an input instance, and every internal node in this decision tree makes a query, typically on one feature of the input instance. And if this query returns positive, we go down, let's say, the left branch. If the query returns negative, we go down, let's say, the right branch. Otherwise, you may imagine this is sort of mathematical equivalent, we swap it around. And then we have some other queries in the other nodes. And we simply traverse this tree until we hit a leaf node, right? And all the leaf nodes have some sort of prediction, right? In this case, for binary classification, the predictions in this case are 0 and 1. They could also be equivalently negative 1 and 1, doesn't really matter. And literally that's all there is to it, right? There's nothing to overthink here. There's no trick that's going on. It is literally just this, right? And all the decision trees, virtually all decision trees look something like this. Potentially very large, instead of just having 3 internal nodes and 4 leaf nodes, it could be much, much larger, right? But that's basically what it looks like, right? And so this particular example, right, we have 2 features. Right? This is the same example as before. And then we have an output variable that's 1 or 0. It's a binary output variable. And for any input instance, I think we have an example in the next slide. Yeah, so we have an example that sort of operationalizes how this decision tree works. Again, don't overthink it. So let's say we have what's called a root node, right? That's where every data point starts, right? These are all internal nodes. The root node is an internal node, and these are leaf nodes, right? And so every internal node has a binary query function. Some people call it Q of X, right, where X is the input instance. And typically, these query functions are just a single feature of the input, right? Every leaf node has a prediction, in this case, 0 or 1. And prediction starts at the root node, recursively calls the query function at the internal node. Now remember, the root node is an internal node. Positive response to the query, go down the left child. Negative response to the query, go down the right child. And you recurse this process until you hit the leaf node, in which case you return the prediction at that leaf node, right? So just here's one example. Suppose this is our input, right? Input instance has there's two features, gender and age, right? And so, we start at the root node, and the query at the root node is whether or not the gender feature is male. In this case, the query returns negative, so we go down the right child, and we query whether or not the age feature is greater than 11. In this case, the query returns positive, so we go down the right child, and then we predict 1, right? That's basically it. So the prediction is yes, the height is greater than 55 inches. Any questions on that? Yes?
How do you choose the order in which to go to the individual features?
Right, so how do we train a decision tree? We'll talk extensively about how to train a decision tree in this lecture. Right now, let's think of this as a decision tree that's already been trained, right? Yeah. Mm-hmm.
Can you explain why it's a recursive call? Because isn't the query function different each node?
Right, so it's recursive in the same sense that traversing a graph or traversing a tree can be defined recursively. There is, of course, if you've taken data structures, you know that you recurse a linked list, right? And you have a pointer to the node in the linked list that you are at, but it's the same function, right? So it's the same notion. And in fact, recursion doesn't make any sense if nothing changes in the state variable that you're recursing, right? Then it doesn't do anything. And here, the recursive, the state variable that changes in the recursion is which inter node you're at. Right, so if you've taken data structures, like some sort of tree data structure or linked list data structures and things like that, this is implemented exactly how you might expect it to be, right, in practice. Okay. So, a decision tree is defined by a tree of queries, right? A binary query, so most decision trees used in practice are binary decision trees, which means the queries are binary, return binary outputs. In this case, let's say 0 or 1, right? So a binary query maps features, so X denotes the feature vector, to some a value between 0 and 1, exactly 0 or 1, excuse me. And the most basic form typically looks at a single dimension of the feature vector, as I mentioned before. So, they take the following functional form. So it's an indicator function of whether or not the D feature is greater than some threshold C. So all the queries, can be parameterized by a D and a C, right? Which dimension of the feature you're looking at, and some C, right? So these are just a few examples, right? In the case where X is, right, in the case where X is discrete, like 0, 1, then it's just whether or not X is non-negative, right? Or non-zero. And you can think of, so a decision tree is in the model class for a decision tree is basically the class of all functions that can be represented as a tree of such queries, right? And therefore you can think of decision trees as the class of axis-aligned partitionings of the input space. And I'll sort of explain pictorially what that means in the next slide. But right now, any questions on the form of the query function? Okay, suppose we're in a two-dimensional space. So a two-dimensional feature space. Here's some training examples. We have positive, negative examples, and negative examples in this two-dimensional feature space, right? Let's say our query at the root node, right, splits the first, the y-axis feature, right, the y-axis feature along this value. So if the y-axis feature, the vertical feature, is greater than this value, we go down, let's say, the left node, the left child. If the vertical axis feature is below this value, let's say we go down the right child, right? And then, on the left child, let's say this decision tree splits along the horizontal axis feature, right? And so if the horizontal feature is greater than this threshold, then we go down the, let's say, right child, doesn't really matter, or otherwise go down this child, right? So each of these corresponds to an internal node of the decision tree, each of these partitions, right? And then we could sort of recursively define things, right? So, within the right, or one of the childs of the root node, this internal node corresponds to all the data in this partitioning of the input feature space, right? And then we can recursively partition that data by creating another binary decision tree grounded at this node. And so this process continues. Right? And then if these are the leaf nodes, right? So this is a depth 1, 2, 3, 1, 4. This is a depth 4 decision tree, right? So we have 16 leaf nodes. This is about this one happens to be a balanced tree, so we have 16 leaf nodes. They're not always balanced, and so these are the predictions. And in this particular case, right, we're just predicting for each leaf node the majority class, right? So this leaf node has majority class is negative. In fact, all the examples are negative, so we're predicting the negative label. This leaf node, the majority class is positive, so we predict positive. Right, so this is just a pictorial representation of a balanced depth 3 binary decision tree over input space of dimension 2, and it just looks something like this, right? So it's an axis-aligned partitioning of the input space. And the function class basically maps things like this to 0 or 1, at least for binary classification. Any questions on that? Yes?
What's a balanced decision tree?
A balanced decision tree, it's the same concept as you would have encountered in data structures. I don't know what class number that is yet. I think it's CS2. Is that right? Yeah, CS2. So a balanced decision tree is simply one where it's balanced, right? So an unbalanced decision tree. Sorry, I don't teach CS2. I don't know the right way to explain it. But let me just give you an example, right? Unbalanced decision tree is one where this is a leaf node, right? And these are not, these don't exist, right? That's an unbalanced decision tree. Yes, I like teaching tautologies. This example is also balanced because every child, every internal node has 2 children, right? Yeah. So in particular for balanced trees of depth 1, it has exactly two leaf nodes, of depth 2 exactly 4, 8, 16, right? They have exactly powers of 2 leaf nodes. Yeah. Yes? I'm sorry, I can't. Sorry, can you speak up? Yeah, so this particular example, just because for visualization purposes, it's a 2-dimensional feature space. More generally, you have some high-dimensional feature space that you can partition along any of those dimensions.
How does here repeat kind of iterates through 2 features?
That's right. So you can partition along a feature dimension multiple times, right, as you traverse down the tree. So how does one know how to do this? Okay, so that's part of the learning algorithm. Determining what's the partitioning that minimizes some training error is the learning algorithm. We'll talk about that later on in this lecture. Yes?
But I'm still confused about your definition of balance. I thought it's like the height, the first I1, not some power of 2. That's not complete tree.
I mean, a complete tree is perfectly balanced, right?
That's right.
Yeah. So, I mean, balance simply means that if the 2 subtrees, right, rooted, I guess there's no universally agreed upon definition of balance, but like qualitatively, it means the 2 subtrees rooted for any internal node, in particular the root node, the 2 subtrees rooted at their children, right, have approximately the same number of same size, and that definition is sort of recursively true throughout the tree. So that's what balance means. It has nice properties. For example, a balanced tree, right? If you have, let's say, some number of nodes, like k nodes in your decision tree, and it's more or less balanced, that means most of the time, the query complexity is log k, right? Because it's balanced. If it's unbalanced, then the query complexity can be linear in k, right? So you would like to have balanced trees because it minimizes the query complexity, for example. Yes?
Are there decision trees that make partitions that are not aligned with the axes?
In theory, yes. In practice, no. It just doesn't buy you much, and it increases the training time, as we'll talk about later. Yeah. Okay. So what I described to you is the function class that is associated with these types of decision trees is a piecewise static function class, right? We get these partitions of the input feature space, and then within this partition we make a constant prediction, right? So it's a piecewise constant or piecewise static function class, right? All possible partitions over the feature space, and each partition has a static prediction. In this particular case, the partitions are axis aligned, so no diagonals, right? We're not conditioning on more than one feature at a time, right? Let's talk about decision trees versus linear models, right? Decision trees quite clearly are not linear models except for very degenerate cases, right? In this particular example, right, if we have two features and these training examples look like this, there does not exist a single linear model. There does not exist any linear model that could achieve zero error on this on this exemplified training examples, right? But a very, very simple decision tree can achieve zero error, right? And then I just sort of drew it right here. It corresponds to the partition you see on your right. Right? So decision trees are more powerful in terms of what they can model than linear models. What kind of functions they can capture, right? Here's another example. This is a kind of a contrived example, but you see no linear model can achieve zero error on this training set because the negative example somehow sits between the positive examples, and yet a decision tree, again, a very simple decision tree, can achieve zero error on this example, right? And here is the sort of the decision tree in diagram form. And again, this tree is not balanced. And we actually recursively, or in the recursion, we query the same feature dimension twice in this example. Now, just because decision trees, in this way, is a very powerful function class, it can model things that a linear model cannot, doesn't mean that they're always more convenient to use, right? So, decision trees, at least the class of decision trees we were going to focus on right now, they are axis aligned, right? Which means even though they have the ability to model things like diagonals, right, it is hard for them to do so, right? So, for this example, right, a simple linear SVM or any kind of linear model can easily find a good hyperplane that separates out the positive and negative examples. A decision tree might have to look something like this, right? So, decision tree you can train a decision tree that can model this data pretty well, but it's just a lot more complicated, right, than a linear model. And if you think about it a little bit more, there are a lot of boundaries in this decision tree in terms of the modeling, right? The decision tree model sort of encapsulates all these different boundaries that are somehow wasted in terms of the making predictions. Right? Yes.
Why don't you just have a linear model be your question in the decision tree?
The reason comes down to training, right? And we'll talk about the training. It'll become obvious once you look at the training algorithms. Yeah. Right, so here's just a very extreme example, right? Okay. So decision trees are often, in fact almost always, more accurate. The nonlinearity is often very important in order to get this high accuracy. You just make a very, very big decision tree, right? And in some sense, it's okay to waste some model capacity on these sort of really zigzaggy boundaries, right? The catch, of course, is that for a function class as expressive as decision trees, we require a lot of training data, right, to train them. So here's an example of a real-world decision tree. I lifted this diagram from a biomedical paper. In applications that I work on for my research, they can get much larger than this, right? They can have thousands of internal nodes. This one probably has something like 20 or 30, right? Another nice property of decision trees, as long as they're not too big, right, this is still okay, is that decision trees are fairly interpretable, right? So you can actually look at this diagram and actually look at what the decision tree is doing. Okay, so now we're going to talk about training. So a lot of the questions that have been asked so far have to do with how decision trees are trained. And once we understand how the decision trees are trained, then some of these questions will sort of make more sense, or some of these uncertainties will make more sense, right? And so let's talk about decision tree training. So as you recall from one of the pictorial examples from before, every internal node, right, or every node, literally, every node, including both the internal nodes and the leaf nodes, correspond to some partition of the input space, which therefore means it corresponds to some partition of the training data, right? So, if every example of your training set will go through the leaf node, right? Some fraction of the training set will go down this internal node, and the other remainder will go down this internal node, right? And in particular, for every cut in the decision tree, for every cut in the tree, the union of all the training data that goes through that cut is the training data, right? Is all the training data. So all of the training data goes to one of these 4 leaf nodes. All the training data goes to one of these 2 leaf nodes or this internal node. All the training data goes through one of these 2 internal nodes. All the training data goes through this root node, right? So any cut you define within this decision tree defines a complete partitioning of the input feature space, and hence a complete partitioning of the training data. Right. Does that make sense? Any questions on that? Okay, so here, let's go through some examples, right? So the entire training data will go through the root node, right? If we look at individual examples, right? So half of this data set will go down the left internal node in the first layer, and the other half goes down the right internal node, right? So here's a thought experiment. What if we just had one node in this decision tree, right? So the root node, I guess in this case, the root node is a leaf node, not an internal node, in this degenerate case, right? There are no queries, right? And we're just going to make a single prediction for all data, right? For every location in our training data in our input feature space. In this case, we'll predict the majority class by a 4-to-3 vote. The positive label is the majority class. So we're just going to predict 1 always, no matter what the input space is, right? So that corresponds to anywhere in the input space, we're going to predict the positive label, right? And so the simplest decision tree is just a single root node, which is also the leaf node, that corresponds to the entire training set and makes a single prediction, which is the majority class in the training set. Okay? This is very analogous to just learning the bias term in a linear model. So what if we had 2 levels, right? So what if we had a decision tree that had a single query at the root node and then 2 leaf nodes, right? So then if we commit to this architecture in our decision tree, right, just a single query plus 2 leaf nodes, right, then the learning question that becomes, how do we pick the query, right? So any guesses on how many possible queries there are? We'll go through an example. Right, so suppose we have a 2-dimensional feature space. Again, this generalizes to multiple higher dimensions. We're just looking at 2 dimensions because we can visualize it, right? And so, you know, let's just brute force it, right? So we're gonna consider, you know, maybe this one as a partition, maybe this guy is a partition, and maybe this guy is a partition. And remember that every time we consider such a partition, it's easy to determine what the prediction of the 2 proposed leaf nodes are, right? It's just the majority class of both, right? And then we'll do the other dimension, right? I had a lot of fun making these slides. Not. All right. So all possible queries equals all possible splits of the training data, right? Anytime you could possibly have a different type of different prediction of leaf nodes is when the threshold passes through one of the training examples. Otherwise, you're going to get the exact same predictions, right? And so if there are D features or D dimensions, right, and N training points, right, then you have capital N points or capital N minus 1. You know, I'm not counting it off by 1. On the order of D times N. So you have to order on the order of D times N possible splits, right? So it's linear in the number of features, and it's linear in the number of training examples, right? So if we were to brute force this for a simple decision tree with a single query and 2 leaf nodes, right, we would just, you know, brute force this. All right, so the final question then is how do we actually choose the best query, right? So what this procedure that I described will be applied recursively in decision tree training, and I'll go through a complete example of how that works. It's called basically top-down training, where we recursively partition the training example in a greedy way by looking at all possible partitions of the training set that is partitioned to that node, right? In the beginning, with just the root node, 100% of the training set is partitioned to that single root node, right? And then we sort of do basically loop through all possible sub-partitionings of the data that goes through that node, and then we choose the best query, right? And the choice of the best query depends on what's called the impurity of the data in this leaf node. The impurity is highly related to a loss function. It's just the people who worked on decision trees, you know, before the communities all merged together into what's now known as machine learning, they called it impurity. You can just think of it as a loss function. Okay. So you know, the impurity that we ultimately care about, you know, in the case of classification, is 0-1 loss, right? So you can think of this as, you know, if we assign a label to the leaf nodes, right? You know, what is the classification error, right? So how many data points are in this node that belong to the minority class, right? So, you know, and most of you can probably see where this is going because 0-1 loss is, you know, flat and discontinuous everywhere, but you know, let's just go through an exercise. Yes?
What is the notation S prime?
S prime denotes some subset of the training set. So every leaf node or every internal node corresponds to some partition of the training set. So I use S prime to denote some subset of the training set. Yeah, because you can in decision training, we can equivalently think of a node as a partition of the training set. Yeah. So here's the whole training set, right? And if we just had a single root node as a leaf node, we're not doing any splits. We just predict the majority class. So the impurity as calculated by 0-1 loss is 1, right? And we can also normalize if we want to divide those normal training examples. It doesn't really matter. If we sort of make this partition, right, this guy right here, so now we have a decision tree of depth 2 with a single query and 2 leaf nodes. And we predict the majority class in the 2 leaf nodes, right? So this leaf node corresponds to these 2 training examples. This leaf node corresponds to these 3 training examples. We still have an impurity of 1, right, as measured by 0, 1 loss. And the impurity reduction is 0. So as measured by 0, 1 loss, we get no benefit from making this split, right? If we do this, if we do this as our split, right? Again, we still get an impurity of 1 even with this more complex decision tree, right? So no benefit from making this split, right? And of course, in this very simple example, there exists a single split that takes the impurity from 1 to 0, right? And so decision tree training basically says we consider all possible splits of this node, all the training data that corresponds to this node, and we're going to choose the split that gives us the largest reduction in impurity under some impurity definition. Here we're just sticking with a 0, 1 loss as impurity for now. So right, so you can think of impurity as analogous to the loss function, as we've talked about in class so far. As I mentioned before, impurity was a term that people who worked on decision trees used before the field sort of coalesced into what's called machine learning these days. So a lot of times you'll have a lot of terminology from different sort of groups of researchers so therefore you have names that are not consistent always. But just so you're all aware, if people work on decision trees, call it impurity. So the impurity over all the leaf nodes, right, is the training loss, right? So if S prime iterates over the training sets that are defined by the partitioning with respect to the leaf nodes, right, then the impurity of your decision tree is equal to the sum of impurities of your leaf nodes. And the impurity of a leaf node, right, is simply as defined by the 0, 1 loss, right, is simply you just take the majority class, so that you minimize the prediction, the sum of the minority class, right? Okay, so what's the problem with 0, 1 loss? So here's an example. This example is not linearly separable. And so what happens is, no single split of the data, right? No one split of the data moves the impurity from 1 to 0, will decrease the impurity, as if you measure impurity as 0, 1 loss, right? I mean, you could do the exercise yourself, but because this particular data set is not linearly separable, no single split of the data will change the 0, 1 loss from 1 to 0. Right. So all partitions give the same impurity reduction, in particular 0. Right. This is the same as the problem we encountered before, right? 0, 1 loss is flat and discontinuous everywhere, right? And even what might look like a good partitioning, right, may not improve the 0, 1 loss, right? So this partition is actually pretty reasonable, because if we just do one more partition on this guy, on this guy, we get perfect 0, 1 loss, right? Perfect accuracy. But a greedy, just looking one step ahead, maximal reduction in impurity will not get us there if we measure impurity using 0, 1 loss. We'll get stuck. So let's talk about surrogate impurity measures. Actually, before I do that, I should just mention that the reason we do greedy top-down induction is because exact training of a decision tree, right, is either NP hard or sharp P hard. It's very hard. So we do greedy train. Yes.
In the L of S prime for the leaf nodes,
Yes.
why do we minimize over which feature we're considering? Like here, we're just considering y, right?
Right, so if in a leaf node, we're not splitting the data anymore. We just simply predict the majority class, which is equivalent to minimizing this loss function. Choosing y, the prediction of this leaf node, that minimizes the loss in all the data set that partitions to this leaf node. Yeah. Okay, so let's pick, so if we want to do greedy top-down induction, training of the decision tree, where we recursively split a leaf node into an internal node with 2 leaf nodes, and we want our decision criteria to be chosen greedily, right? Defined greedily. Then let's think about surrogate impurity measures, right? So in some sense, we want a more continuous impurity measure. Here's one example. It's called Bernoulli variance, right? And so it's defined as the, so let P of S prime be the fraction of S prime. Recall S prime is some subset of the training example that corresponds to a leaf node, or any node, right? So P of S prime is a fraction of S prime that are a positive example, right? And so then the Bernoulli variance is simply, P times 1 minus P, right? That's a standard variance under the Bernoulli distribution. Will scale by the number of examples so that nodes that have more training data are weighted more. And so then you could think of this as an impurity measure, right? And so the worst impurity is when the fraction is exactly 1/2, right? In that case, it's the number of training examples in this partition divided by 4. And the best impurities are when it's either 100% positive examples or 100% negative examples, in which case the Bernoulli variance and the impurity is 0, right? And you get a curve that looks like this, right? Yes?
The optimization still combinatorial?
Well, we're going to do greedy top-down induction, right? So we're going to greedily grow this decision tree top-down. So we're not going to do the full combinatorial search, but we want a criterion to commit to a split, even in top-down induction, that is somehow more continuous than 0-1 loss. So let's go back to this example, right? So in this example, if we just consider the whole training set, the impurity is about 5/6. If we consider this split, right, the impurity of the left side is now 0, right, because it's all positive, and the impurity over here is 1/2. And then, if we consider this split, right, the impurity on the left child is 0, but the impurity on the right child is 3/4, which is higher than this guy, right? So if we want to maximally reduce the impurity, right, if these are the two that we were considering, we would choose this split over this split, right? Even if we're just doing greedy, myopic top-down induction, just choosing one split without thinking about future splits. Right, so this would be the best split. Right. So Bernoulli. If we take if we try to interpret what Bernoulli variance is doing, right? Then basically we're basically saying that we're going to define a piecewise static distribution over the labels, where the partitioning of the piecewise static partition is a function of the input features, and then within each partition, the label is Bernoulli distributed, right, with some probability of being positive and some probability of being negative, right? And so the goal, if Bernoulli variance is our impurity measure, then the goal is to find a partitioning where the distribution has low variance, right? So there are other impurity measures. There's entropy. Again, it's a function of the fraction of data points in that partition that is positive, right? It's also which is also known as information gain. If you want to minimize the entropy as you grow your decision tree. This one is one of the most popular ones. It's arguably the most popular impurity measure, at least for classification. There's other things like the Gini index. One thing to note is that they all more or less have the same curve, right? right? They all have this like this concave curve, right? Inverse quadratic shape to it. So they're all qualitatively very similar. These curves, these impurity measures have a maximal value at 50-50, and then have go to 0 as you go to 100% impurity, right? Yes?
Can you use this variance value to set the stopping area?
Yeah, so I will, I'm going to get to that in a couple slides, I think. But let me just sort of go through the whole top-down training procedure, right? So, we have a definition of impurity measure that's smooth, that we like, such as Bernoulli variance. And then basically top-down training just says we have our current decision tree, and then we choose the split over all leaf nodes that has the greatest reduction in impurity until some stopping condition, right? And so step 1, we just have a single root node, right? We start with a single root node that corresponds to the entire training set. We make the prediction of +1 because it's a majority class, and we compute the impurity of this decision tree, right? It's right here. And then step 2 says, okay, let's try to split the data in the root node according to one of the access line features, and then we compute the impurity, the sum of impurities of the resulting leaf node, 2 leaf nodes, right? And so we loop over all possible, and so this is the best possible split. And then now we recursively say we loop over all the leaf nodes, and we consider all possible splits of all the leaf nodes, and we commit to the split that has the best reduction in impurity, right? So we try this guy, we try this guy, we just go through a for loop over all the possibilities. Again, the number of training examples is conserved, right? It's still capital N across both leaf nodes, and there's d dimensions, so this is still a d times n operation. Right, and then we just keep doing this until we have this decision tree that satisfies some stopping conditions, and we're done. Any questions on that? Yes?
So how are you deciding which features to split on here? Are you also looking over the features?
Yep, you loop over all features, so there's capital D features, there are capital N examples. Even if we were looping through these two, both of these 2 leaf nodes, the number of training examples is still conserved at capital N. So it's still a d times n operation at every layer. Yes?
Follow-up question on that is that how do you like first do you ask make a query about age first or
So,
purely prediction first based on that and then prediction based on age? How do you know?
you loop through all possible partitions, and then you pick the one that has the highest impurity reduction.
So here we ask the question first about that and then ask the question about age.
So when you are recursively doing this top-down training, you don't care what questions you asked before to get to this partition. For every time you recursively call this top-down training procedure, you're given some partition of the training data. You're at one of the nodes that's currently a leaf node, and then you just try all possible queries, and then you pick the one that gives you the best impurity reduction. You don't care, the queries you've asked before. That's sort of, it's sufficient just to consider the training data that gets partitioned to this node.
So I think the question is, does the order matter?
Does the order matter?
Yeah, for example, if you pick age first, and take male second.
You mean here?
Yeah.
Yeah, it does matter. That matters. When you're training one of these nodes, you consider all possible partitions. But yes, the order does matter, and so maybe it'll make sense if we sort of go through an animated version of this training process, right? So we loop through all possible partitions for the root node, right? And for each time we do this, we measure the impurity reduction. If we were to potentially make a different prediction, in this leaf node versus the other leaf node, versus just making a single prediction over the entire training set. and then we commit to this split, right? Let's say that this is the split that gives us the greatest impurity reduction, right? And then we start, making potential splits of one of the two leaf nodes, right? And we consider all possible splits over all the leaf nodes. In this case, there are two leaf nodes. Right? And we commit to that, right? So, very rarely would you be able to get the exact same partitioning if you swap the order. Like the only case that you would is if on this leaf node you also divided the data exactly here, right? Then the order doesn't matter. But otherwise it does. Right? Yes.
So since we just scanned over all possible partitions over both of the rectangles, wouldn't we now sort of have a good dividing line for the lower one as well?
That's right. You don't need to redo computation. Sometimes you don't commit to that partitioning because committing to that isn't good enough. Maybe it's stopped because it just says you don't need to. Right? So the more partitions you have, the more complex the decision tree is. So a lot of times you don't commit to making that partition, even though you've already done the computation for it. You don't commit to it because it's not worth it under your stopping condition.
Okay.
Yeah.
How do you deal with overfitting? It seems like we've gone all the way to 0 loss.
That's right. So let me. I guess no one wants to see the remainder of my animation. But let's. I'll get to some properties of top-down training, then I'll talk about stopping conditions and overfitting. Okay. So every intermediate step, just to summarize what we've seen so far, right? Every intermediate step is a decision tree. Right? You can stop this top-down training algorithm anytime you want and have a valid decision tree, right? This is a greedy algorithm, so it doesn't backtrack, right? So it doesn't say, oh, I think I made a mistake. Let's like revert some of these splits and try a different split. We don't do any of that. So in that sense, this is a greedy algorithm, right? And so now the question now is when to stop. How do we? Yes.
Go back. In theory, there's like n times d possible partitions. In practice, do you consider all of them? You said that you need a large training set.
So when the training sets are really big, in practice we subsample the possible partitions. It doesn't really matter if we sort of tweak one, right? Tweak it by one. So if you have like a billion training examples, you typically don't consider all possible 1 billion splits. You just subsample maybe like 1,000 splits along each dimension, something like that. Yes.
So kind of going off that, I noticed that there was like a male and female thing, which is like binary, so it's 0, 1, so instead of 3, 2 there. But in general, would it make sense to like kind of like make like a continuous feature binary in order to like make
So decision trees certainly train a lot faster if you flag a feature as an indicator feature rather than a continuous value feature. Right? So if the decision tree training software, if it knows that this is a binary feature, it can be much more efficient about how it trains. Yes. That's sort of more of an implementation detail, but yes, that's right. Yes. That's right. There is no online learning algorithm for decision tree training. That's right. At least not a good one. Yes?
How do you pick where exactly to put the split? Because it won't affect impurity, but if you use it...
So people typically put it in between two training examples. So if this has some feature value A, this has some feature value B, you do 1/2 A plus 1/2 B. Like in the absence of further information, that's somehow the best you can do. Yes.
How well does decision tree do when the predictor is a factor, example 5 factors?
So the predictor depends on 5 features?
No, it's like a certain response of 1 to 5.
Oh, so if you just treat that, you can just treat that as a real value number.
But for example, if the order of responses don't have any meaning,
Oh, okay, so then you can split that into 5 features, 5 indicator features, right? You know, so that's called a one-hot encoding. So if your feature is categorical, right, categories A through C, right, and the categories themselves don't have any ordering to them, then you can split it into 3 features, 3 binary features, right? Is it category A, yes or no? Is it category B, yes or no? Is it category C, yes or no? And of course, only one of those 3 features will be active at any given point in time, but you know, that's what you can do, and the decision tree training will just work. Most decision tree learning algorithms actually can do that conversion internally, right? So if you have a categorical feature, you just flag it as categorical, and then the decision tree learning algorithm internally will just do the conversion internally. So you don't need to really need to worry about it. Yes?
So if your features are real values, the complexity is going over all of them.
It's the full complexity is capital D times capital N, because there are capital N unique splits of a real valid feature, where capital N is the number of training examples. Okay, now let's talk about when to stop, right? Obviously, you can, I can split this data ad nauseum, where every leaf node has exactly 1 training example, and I would get 100% training accuracy, right? That's possible. Obviously, we want to do that. I mean, I think we all have an intuition that that would overfit to the training set, right? But how do we actually sort of, you know, more systematically determine when to stop? Right, if we kept going, we could always learn a decision tree with 0 training error. Unless 2 examples were exactly superimposed on top of each other, we can always learn a decision tree with 0 training error. Right? Such a tree is probably going to be overfitting. Right? So, how do we regularize decision tree training? Right? So there's a few stopping conditions. Right? One is minimum size. So, you know, do not split the decision tree. For any current leaf node, do not split it if it causes a partition of a subsequent leaf node to be smaller than its minimum size. This is one of the most popular stopping conditions. It's the one that I tend to use in practice. Some maximum depth, don't split if the resulting children are beyond some maximum depth of the tree. Maximum number of nodes, not split if the tree already has some maximum number of allowable nodes. Minimum reduction in impurity, right? Do not split if the resulting children do not reduce the impurity by at least some fraction, right? So even though, you know, as someone asked in the front, you know, we've already pre-computed the possible splits of all the leaf nodes, right? These are reasons why we may not commit to such a split, even though we've already done the computation. Okay, and I'm going to skip through this in the interest of time, running a little bit behind schedule, but this is some pseudocode, right? It is literally what it, like, this is basically similar to what you would look at in CS2, just some binary split data structure with pointers and leaf and children nodes, and each term node corresponds to the partition of the training data, and then you just grow this data structure as the training on top down. Classification versus regression, right? In classification, all the labels in the leaf node are 0 or 1. In regression, the labels are real value. In classification, in each leaf node, we basically just always predict the majority class. In regression, we predict the mean of the target labels in the leaf node, right? So in both cases, these are piecewise constant function classes. The ultimate goal of classification is to minimize 0, 1 loss. In regression, it's typically to minimize squared error. And impurity for classification, some smooth function based on fraction of positive versus negatives in the leaf nodes, such as Bernoulli variance or entropy. For regression, it's actually much simpler. It's just squared loss. So squared loss is itself a continuous and differentiable function. But otherwise, the training algorithm is exactly the same. Okay, so just to recap on decision tree training. You know, we train it greedily top down. Goal is to greedily minimize some definition of impurity, which you can think of as equivalent to training loss. until some stopping condition is met. Finding the optimal tree is a combinatorial problem. It is computationally intractable under standard complexity theory assumptions. Okay, so just to recap the decision trees, we have a piecewise constant model class. We train and minimize impurity, and is often more accurate than linear models. In the remaining about 25 minutes, I want to talk about bagging, right, which stands for bootstrap aggregation. And so we're going to do a quick recap of the bias-variance trade-off, because bagging is motivated by the bias-variance trade-off. Then I'll talk about bagging, and then a simple extension to bagging called random forests. Okay. So recall that our goal is to minimize test error, which is the error over the true distribution, or the test distribution, which is unknown to us. We're given access instead to a training set, a finite training set of XY pairs that are sampled IID identically independently from the test distribution. Right? And our goal somehow is to try to minimize test error, right? Which is the expected error over the test distribution, even though we cannot directly measure it. Right? And overfitting is when test error is much higher than training error. Right? And training error is the error over our finite training set. And so, typically, we have our training set, right? And then, which is drawn independently from some true test distribution, right? And then, we, make a prediction. Here's the true label. We make a prediction, and we, get some of them right, some of them wrong. And how does that relate to testing, right? So, one thing that we talked about in terms of getting a handle on, reasoning about test error is the bias variance decomposition. Right? For squared error, the bias variance decomposition has a very simple, basically closed form formula, right? Where the expected error on the test distribution decomposes additively into a variance term and a bias term. The bias term is the difference, is a squared error between the average predictor, where the randomness is taken over the randomness of the training example. So if you were to collect multiple training sets of the same size, each sampled from the test distribution, and train multiple models, and then average their predictions together. If this is a thought experiment, of course, then this is the bias term, and the variance term is the variability of any individual model that you might train, and how it deviates from the average model, right? And so it's just an example in one dimension. We're doing one-dimensional regression. We've all seen this before. This is a test distribution, right? If we were to do linear models where we subsample 7 data points at random from the test distribution and train a linear model, right? This would be the variability we get. For quadratic, this is the variability we get. And for cubic, this is the variability we get. Right? And then we can explicitly measure the bias variance trade-off in this simple example, where the bias is the deviation of the ground truth label, which is the vertical, which is the y value, right? This is a one-dimensional regression, versus the black line, and the variance is the deviation, the variance basically of the prediction at these points from the black line, right? Of an individual model. Right? So let's just skip this in the interest of time. We've all seen it before. And so let's think back on bias variance for decision trees, right? If this is our decision tree trained on the training set, right? And this is the sort of true test distribution with a bunch of data points that we haven't seen, right? The hope is that we'll get most of those classified correctly as well, right? And so decision trees are low bias, high variance models, unless you regularize a lot, right? Highly nonlinear, can easily overfit different training samples. Right? If we took a different sample of the training set, can lead to very different trees, right? So that's where bagging comes in, right? The goal of bagging is to reduce the variance of high variance models classes, such as decision trees, right? So here's the bias variance trade-off, and here it's just the expected error on a single test example. Right? And it decomposes into this bias term and a variance term, or just that definition. In the ideal setting, right, if we somehow magically were able to collect multiple training sets, right? And I'll call those S prime. We'll train a model on each S prime training set, and then we'll average their predictions, right? What will that do? That will drive this variance term to 0, right? That'll drive the variance to 0, right? If the training sets S prime were sampled independently. This is just standard probability 101, right? Right, the variance reduces linearly as we somehow collect more training sets of the same size, train a model, and average the predictions of all these models together. The variance reduces linearly. Again, this is probability 101. The bias is unchanged, right? Of course, in practice, we can't actually collect a new training set, right? That's just not possible, right? And so in practice, what we'll do is we'll sample S prime with replacement from S. S is our original training set. We'll just sample S prime with replacement from S. We'll train a model on using each S prime, and then we'll average the predictions. That's what bagging is, right? Bagging stands for bootstrap aggregation, and this process of sampling with replacement is called bootstrapping in statistics. Right, so we have our true test distribution from which we collected the training set S, and then we're going to bootstrap from S to create S prime, which basically means sampling with replacement. Right? And for each S prime, we'll train a decision tree, in this case, and then we'll average the predictions of all these decision trees to form our final predictor. And that is bagging. Right? And of course, because we're doing this bootstrapping, right, the variance will not be reduced linearly because we're not sampling these things completely independently from the test distribution. We're sampling from S, and not exactly the test distribution. And so this will not cause the variance to go to 0 as it would in the ideal case, but in practice, oftentimes, at least with high variance models, it will cause the variance to decrease. Right? So here is just basically a recap of bagging for decision trees. So you have your original training set S. We're going to generate many bootstrap samples, S prime, or S prime is a training set of the same size as S, but every example is sampled with replacement from S. And we're going to do this many times, let's say 500, right, or 100. And then we'll train, relatively minimally regularized decision tree on S prime, right? So, we don't want this decision tree to be regularized a lot because we want high variance, low bias models, right? And those are minimally regularized decision trees. And then the final predictor is the average prediction of all the decision trees in our ensemble of decision trees. In the case of regression, that's literally an average. In the case of classification, it's the majority vote. Right? And the intuition of why this works is that averaging reduces the variance of the model class. Right? And so here's one empirical analysis from this paper, where they're looking at the original decision trees versus 3 different ways of doing bagging or trying different types of decision trees. And they can actually, in this case, they can decompose the loss into bias, which is the horizontal bar part of the loss, versus variance, which is the diagonal bar part. And you can see that the variance went down, the bias, in this case it went down a little bit, but typically they stay about the same. Right. So why might bagging work? Right? Is there some sort of more mathematical way to sort of understand why bagging might work? Right? So in the ideal aggregation setting, not bootstrap aggregation, each S prime is drawn from the true test distribution, right? So then our aggregate predictor, H of A, right? If we drew an infinite number of S primes, our aggregate predictor, H of A, is basically the average prediction of a predictor trained on some training set sampled from the true distribution. Right? This would be what bagging or the aggregation predictor is, right? So first, let's compare the error of the ideal aggregate predictor versus a single model in a single class, right? And then we'll show to adapt this sort of thought process to bagging, right? And so here's an analysis of the ideal predictor for squared loss. Again, we're going to use squared loss because the bias variance trade-off, it has a trivial or really nice decomposition. I suppose it's not trivial since you have to derive it for your homework. So this is the expected loss of a single S, right? Of a single example, right? I just wrote out this thing by linear expectation, right? Here, the y doesn't depend on the training sets. This y doesn't, so I'm just moving terms around. This is, I wrote out this inequality because moving the quadratic, right, outside of the expectation, moving this quadratic creates this inequality. This is just invoking Jensen's inequality. And this is basically the error of the ideal predictor, right? So I invoke an inequality, and I get the definition of the loss of the ideal predictor, right? And so therefore, you get to a reduction there. And of course, we don't have access to the ideal predictor. We have access to bootstrapped. We don't have access to the ideal aggregate predictor. We have access to the bootstrapped aggregate predictor, right? And so the ideal aggregate predictor improves, if this term is greater than this term, which is equal to this guy. So this is large if each individual H sub s is quote unquote unstable, has high variance. That's when this inequality has a big gap, right? In bootstrapping, right, so we don't sample from the true distribution, we sample S prime from S via bootstrapping, right? And so this improves if the bootstrap predictor is more stable than these individual ones, right? And so this, sometimes, the answer is that this sometimes works, right? And in practice, it usually works, right? But it's not always guaranteed to work because we're not actually sampling from the true test distribution. Okay, so in the remaining few minutes, I'm going to talk about random forests. So the goal again is to reduce variance, right? Bagging can only do so much, right? Resampling from the pre-collected training set will asymptote, right? Random forest says, okay, well, let's not just sample individual data points, right? Let's sample both data points and features simultaneously. That's what random forest. That's the intuition behind random forests, right? So we're gonna sample. We're gonna generate a bootstrap sample S prime, right, of the original training set, and then we're gonna train a decision tree on S prime, right? But while we're training the decision tree, we will not allow all the features to be selected, right? So what does that mean? That means that as we're doing top-down training, for each internal node during top-down training, we're going to sample a subset of the features that are allowable. And you can only do the top-down induction over those allowable features. So you're not allowed to loop over every possible feature. You're only allowed to loop over a subset of the features that are sampled randomly at every internal node during top-down training of the decision tree. And the intuition is that this will further decorrelate each individual decision tree in the ensemble of decision trees, which means that when you average them, you're getting more information. So, and this is the only difference, right? Otherwise, it's the exact same process as bagging, right? So, we're going to, there's a few different variant ways of doing this, but we're going to to sample T random splits at each leaf node. We'll choose this split with various impurity. Typically, these splits are constrained to a subset of the features that are also sampled at random at every leaf node. Right, so we have the original root node. We randomly decide only to look at H when training this decision tree, right? For considering how to split this node. Of course, this type of process is kind of meaningless for this simple representation, but sort of it's the idea I want to convey. Right, and so we look at H, right? We choose a split on H, and then we have this. We choose the best split on H that we were allowed to choose, and then we have this decision tree, right? And then when we are considering splitting this leaf node into an internal node with 2 leaf nodes, we randomly decide only to look at gender, right? We have some random process that says which features are allowable. In the simple example, where there's 2 features, we're just going to choose one of the 2 at random, right? And then we try to split. This doesn't do much, right? And here, we're going to randomly, when we consider splitting this leaf node into an internal node with 2 leaf nodes, we're going to randomly decide only to look at H, right? And then we find that split, and this one's pretty good. Right? And that's it. And then we repeat this process for every bootstrap sample of that we've generated, and then we average all the predictions of all the trained decision trees. Yes?
So in this case, the specific numbers 9 and 8 in the H check, those are instances of the T random splits, right?
That's right. Yeah. Was there a question?
Can you explain explicitly what does the bootstrap mean here?
So, right. So the bootstrapping is just like in bagging. We generate a bootstrap of the original training set, which means we sample a new training set from the old training set with replacement, uniformly with replacement.
Okay, so you mean that the data points in sample S prime are the same as in S?
Well, no, you can. So when you sample with replacement, some data points in S prime are going to be duplicates, right? And some data points in S won't be in S prime.
Oh, I see.
Yeah. You're sampling uniformly from S with replacement. So you sample a data point from S uniformly, and then you sample a data point from S uniformly again, until you've created a training set S prime with the same size as S. So some fraction of the data points actually will be duplicates. Yes?
How would you choose the size of S prime?
S prime is typically the exact same size as S. Yes? I mean, the analysis, of course, is at infinity, but no one does that. Typically, let's say 1 to 500. 100 to 500. Yeah. Yes?
What does it mean to average the trees?
You average the predictions.
Oh.
Yeah. You don't average the parameter. It doesn't make any sense. You simply average their predictions. Yeah. You average their outputs. Okay, so just recap. So it's an extension of bagging to sampling features during training, as well as sampling the training set, just like in bootstrapping. This only works for decision trees. You can apply bagging to any high variance model class, and it'll work. With random forests, as presently constructed, it only works for decision trees, right? And so here's an example. So this is a empirical study that was done. This was done almost 10 years ago. And so this is they averaged over a bunch of different data sets with a bunch of different performance metrics. As you can see, random forests are amongst the best performing models over a wide range of data sets in this particular empirical study. So this is actually a very, very powerful model class. Very expressive with a lot of ways to control for overfitting through averaging. Any questions? Yes?
Is there any particular instances in which random forests are not that good compared to others?
Right. So these days, you know, if you want the best performance, typically you would try to use deep learning. In many cases, random forest, the performance of random forest is actually competitive with deep learning, and they're often much simpler to train. Right? They train much faster, especially if you don't have a GPU. I guess it really depends on the individual data set, right? So as you'll discover in the casual competition, mini project 1, you sort of just have to try a bunch of models, see what works best. Okay, so that's it. Next lecture, we'll be looking at boosting, which is the flip side. Instead of trying to reduce variance, we're going to reduce bias. And the presentation next week on deep learning.